My name is Tony. I'm going to be talking to you about the price oracles. I know we're a bit short on time, so I'm going to try to make this concise and drop some auditing alpha too. I'm going to start with showing you the resources that we already have for the price oracles. And so check out the README first, as always, for instructions to clone, build, and test. We also have a white paper, which is going to be a more technical deep dive into both design and implementation of these price oracles. And then also check out the EVK white paper, because it's going to give you an idea of how this code base fits in to the wider stage of the EVK. And finally, I want to point out that we have 5 previous audits of this code base, and I highly recommend you to check out those reports because there's some really good analysis of stuff, and also look at what issues were already found to get some inspiration where to look for to find something new. I guess it's best to start with this iPrice Oracle interface. Now, as the name suggests, this is sort of a library of Oracle integrations and components. And this interface is sort of the centerpiece of it all. So if we take a look at this, let's see, yeah, this is good. If we take a look at this get quote method, you will see that it takes 3 parameters: in amount, base in quote, and returns an out amount. And now basically it works like this. So if you give it 1E18, base asset is WETH and quote is USDC, you expect this to return something like 3,800 E6. So get quote basically answers, what is the equivalent amount of this quote asset to a given amount of this base asset. And so it's a sort of a departure from how oracles usually work. So if you're familiar with like Chainlink, for example, is going to give you what we call a unit price. So it's only going to report, let's say, the price of 1 ETH in terms of US dollars. And you have to do some mathematics on that price to arrive at a quote, a size-dependent amount. And that mathematics is usually multiplying it by the in amount, scaling some of the decimals, and possibly, rounding up or down. Now, you will also notice we have the get quotes method, and Derek alluded to that as well. It returns the bid and ask prices for this asset. And this is how things are actually priced in the real world. If you take any asset on an exchange, right, it's always going to have a price that you can buy it for and a price that you can sell it for. And usually that spread, right, is in the interest of the exchange. So it's either fees, right, or the fact that liquidity is finite, but really that a single price does not capture the liquidity of that asset. And so that's why we think like bid-ask prices are are a good thing to use from a risk management perspective. And so now that we understand the interface, let's take a look at base adapter. This is sort of the abstract base class that all adapters in this repo will implement. Now I'm throwing out some terms here. So an adapter is basically an Oracle integration. So we have a chain link adapter, Redstone, and so on. Or you can think of an adapter as middleware that converts the raw answer to a quote according to iPrice Oracle. And so base adapter is going to be the abstract base class that all adapters in this code base are going to implement. And
to everybody, sorry, just a quick interruption. The sound travels very easily into the conference area. So please, if you're going to have any conversations, there are 2 rooms that are more private. But just to not distract the speaker and the folks that are focusing on the code base itself, if you could just refrain from speaking too loudly, that would be great. Thank you, everybody.
All right, thanks. Okay, back to the base adapter. I'm going to point out 3 things that are relevant here, and you should pay attention because this applies to all adapters in the repo because they implement this base class. First of all, is that this get quotes method that doesn't actually return a spread. This is sad because we really like bid and ask pricing, but unfortunately, most oracles don't support them natively. So we just return the 2 mid prices directly. And then, so when you inherit base adapter, you will override this underscore get quote. And this will contain the logic to like fetch the price, validate it, and convert it to a quote. And finally, the elephant in the room, this get decimals method, which we basically use to determine the decimals of base in quote. And what this logic basically is we try to call decimals, and if it fails, we fall back to 18. We basically do this to be able to support USD. As you know, like most feeds, well, not most, but many feeds are denominated in USD, and that is not an ERC20 token yet. And so we want to have a convention for representing them and a convention for the decimals. And so we have 18, and for the representation of USDC, we use this ISO 4217, which is actually used by Chainlink as well. So it's this, I don't know, international standard numeric code for like currencies, but it doesn't actually matter how you represent it, as long as it's not a contract with code, is going to fall back to 18 decimals. Okay, another sort of infrastructural thing is this scale library. This is sort of a generalization of the price conversion mathematics. So, right, you take the unit price, you multiply it by the amount, and you take into account the decimals of the base, the quote, and the feed. And this is something that you actually have to do for every asset. This is sort of gas optimized, so we have a custom type that is going to contain two price scale components, the price scale and the feed scale. And yeah, you'll see the adapters called this calculate scale method with the decimals, and it will return a scale that it puts in the immutable variables. And then when you're actually getting a quote, right, they use this method for convenience to convert unit price to a quote according to the scale. And we also support the inverse direction. So like if the feed is ETH USD, you can also price USD to ETH. And this is this case. And so, yeah, this is it for like the infrastructure behind the adapters. Now it's time to look at some of the adapters themselves. Now there are 6, 1, 2, 3, 4, 5, 6. I won't be covering the Chainlink or the Chronicle adapter because they're fairly simple, fairly standard and well known. But I want to cover our pool-based oracles, which are going to be Pith and Redstone, because they're more interesting from a security perspective, and this should mean they're more prone to bugs. And so, just to set the stage, how pool-based oracles work, I assume you're all familiar with how something like Chainlink works. So by contrast, right, a pool-based oracle does not give you like an automatic guarantee about the freshness of the price, but in fact you have to basically fetch the price yourself and feed it on chain with your transaction, and so the update flow becomes a concern of the user, and so that makes integrating something like this potentially more sensitive. Pith, how Pith works is actually there's a network of validators that agree on a price, and they push the price updates on PithNet. PithNet is essentially a Solana fork, but when you're using a Pith price on Ethereum, you're gonna bridge that price essentially using wormhole to the Pith sort of master registry on Ethereum. And so what's interesting as well for Pith is the data model. So this is the struct that Pith is going to return. As you notice, there's a price, there's a timestamp, but there are also two other parameters. These are the confidence interval and the exponent. Now the exponent is easy. This is just the precision that this price is in. So it's like for Chainlink it's like fixed, but for Pith it could change, right, depending on the significant digits that we need here. The confidence interval is really unique to Pith in oracles. So it's the statistical 95% confidence interval that for this price, which means that statistically speaking, we could expect the true price to lie in that interval around the mid price 95% of the time. Now, this is actually because, right, your Oracle node is pulling in from different price sources, which never have the same exact price, and rather than collapsing that down to one metric, right? Pith gives you the median price, but also gives you the interval, right? And the tighter the interval, usually, the more confident you are of this price. And you'll see some validation that we do on the pith price. In that, first of all, the timestamp is checked. You will also see that the price timestamp could be in the future here, which is also something unusual when you come across it first. This is because PithNet and ETH are two different networks, and so theoretically there could be like a clock desync. Now the probability of that happening is highly debatable. However, I do want to note that we actually do a stricter check for the timestamp than the Pith SDK, because the Pith SDK enforces a symmetric window around the block timestamp for the inclusion. So if you actually ask it to, wait, I'll show you. If you call this method get price no older than, you're expecting age to be something like 5 minutes, right? And this diff actually gives you the absolute difference of the price and of the publish time and the timestamp. So for some reason they made it this way so that it's like symmetrical around the timestamp, but we override that to one minute in the Pith Oracle. Yeah, also basic checks. The confidence interval shouldn't be too wide, right? It indicates that something is bad. And when you get that struct, you can see we use the scale utils lib to arrive at the quote. And this is Pith. I also want to show you the redstone, which is easily the most complicated adapter that we have, and we went through a lot of design iterations, and we have had a few findings about this adapter. So I'd say, like, if you want to look for something, look here first. Redstone makes it harder. Not harder, but it's more security sensitive, because it's once again a pool-based Oracle, but it doesn't have a global caching registry. So this means for the adapter that it will basically have to act as this registry. And so you will see that this is the only adapter that contains an update price method. So users are expected to interact with this adapter by first calling update price and then calling get quote in the same transaction. And this, by the way, is easily done with the EVC. So you'll see other adapters have this assumption as well, that like the update call and the get quote call are bundled into the same multi-call transaction. So anyways, yeah, update price is very weird when you look at it for the first time. So basically how Redstone Core works is there's a custom data format that encodes the price payload. And the way you update the price is you actually make a normal function and append append this extra payload to message data. So I'll show you, for example, the fork test that we have. So, right, this is the Redstone payload for the feed, and this is the encoded call, right, for update price, and you pack next to that the payload of Redstone. So it's like appended to the data. And we use the Redstone SDK, which is this inherited primary prod data service consumer base. And so, yeah, this method call basically enters into that, and it internally is gonna decode that trailing data as n data packets. And every data packet, it contains a price, a timestamp, and a signature. And so for each one of them, it will call this overridden validate timestamp. It will memorize the price, and after all of it, it will return the median price out of the packets. And so when this code is dispatched, you should imagine that this is called n times, and then price is returned. You should follow the internal call chain in this inherited method to see how that actually happens. And yeah, and as I said, this adapter has to act as the cache, and so there's a cache variable that contains the price and the timestamp of the price. And when you call get quote, right, standard stuff, check the staleness, or otherwise, calculate the out amount for the price. Yeah, we have a few other adapters. I mean, they're fairly standard. We also have what we call a Lido adapter. It's a bit of a misnomer because it's not an oracle per se, but this is basically getting the exchange rate of STETH to wrapped stake teeth. We also have a Uniswap v3 TWAP, which is actually very, very standard implementation of the TWAP. It just this right here is the same logic as Oracle library.consult. Same logic, except for we don't track the harmonic mean of the liquidity because we don't care, but it's basically this unmodified. And yeah, this next to the collection of adapters, we have what we call components. And components are, again, iPrice Oracle, but they are sort of like higher level logic that connects different iPrice oracles. And so one trivial example of that is this cross adapter, which just takes two iPrice oracles and calls them in sequence. And yeah, the canonical example for this is wrap stake these to USD, right? First you call the Lido exchange rate, and then you call the Chainlink oracle. And finally, for today, I want to show you the router, which is sort of pretty complicated. Well, I wouldn't say complicated, but security critical piece of the puzzle here. It's a component that we use in the EVK to price vaults, and is the only I price oracle that is governable. So there is one authorized address that can set these three variables, right? There's a fallback, a list of resolved faults, and a mapping of basing quote to an oracle. And you can think of a router as sort of a dispatcher. So when you call get quote, right, it has some resolution logic that says which oracle to call, and then the router will forward that call to the oracle. So this is the resolution logic. Trivial case, if base equals quote, we can just return the in amount. Then if there's like a direct configuration by the governor for base in quote, right, we can just use that that oracle. And the interesting part is here. The router basically has first-class support for 46 to 26 faults. If you go back to Derek's EVK presentation, he said something that about that. You know, the EVK will be calling the price oracle with a vault, right, as the first argument, the base, and the router, right, will hit this this check and call convert to assets for the in amount and substitute the vault asset in the resolution logic, and begin from step one. And through this abstraction, this router actually supports any level of nesting of vaults. So you could have like wrapped USDC, and you could resolve that to the base asset, basically USDC, and continue from there. Finally, for the resolution logic, we have the fallback oracle, which is basically, as it sounds, like configuration level fallback. So this actually unlocks a pretty cool use case, because you could have a canonical deployment of the router that you trust, and you could deploy your own one, point to it as the fallback, and add your custom overrides to that. And we think it's a pretty cool primitive.